In this video, we're going to go over the concept of free fall. So when we talk about free fall in physics, we're saying that an object is falling only under the influence of gravity. I put falling in quotes because the object could be, you could throw an object up in the air, and if the only force acting on the object is gravity, we would still refer to that as free fall. So let's go ahead and start with an object falling. And this is could be a rock or any other object falling towards the ground. And assuming that there's no air drag, no air resistance, we're going to make down positive. And if we were to measure the velocity of this object, we'd notice that the velocity would increase as it falls. And if we calculated the acceleration, we would find that whether it's heavy or light, as long as there's no air drag or no other forces other than the force of gravity, that the acceleration is going to be 9.8 meters per second squared. Now this is a very special number, so that oftentimes we will use the symbol G to refer to that number. And so also to kind of make it easier to think about this conceptually, sometimes we'll round this to 10 meters per second squared. So let's create a data table here for this object falling. So we have time in seconds and velocity in meters per second. And we're going to go up to 3 seconds here. So when we say that an object has a downward acceleration 10 meters per second squared, we're saying that every second it's going to increase its velocity by 10 meters per second. So 1 second later its velocity is 10 meters per second. 2 seconds later is 20 meters per second. 3 seconds later it is going to be 30 meters per second. Okay. Now, let's take a look at, we're going to go ahead and draw a little picture of this. You can imagine someone on a really high cliff here and dropping an object. As it falls, it's going to fall faster and faster and faster. So initially it has an initial velocity of 0 meters per second. Then if we make down positive, 1 second later it has a velocity of 10 meters per second. 2 seconds later it's going to be 20 meters per second. 3 seconds later it will be 30 meters per second. And these will be positive because I'm making down positive. And just to remind us that the acceleration due to gravity is always downward. Now I'm going to draw a velocity versus time graph. And if we were to draw an object falling in free fall, we would get a graph that looks like this. The reason it is at positive velocity is because we are making down positive and it's moving in the positive direction. If we calculated the acceleration, or if we calculated the slope, we would get 10 meters per second squared, which is what we would expect because the slope on a velocity graph represents acceleration. Now this acceleration is also true for if you were to throw something straight up into the air or launch something straight up into the air. So let's say we were to shoot something into the air, and as it goes up it's going to slow down, and as it falls back down it's going to speed up. And let's assume that there's no air drag, so this is in free fall. At the highest point, we would say that the velocity is 0 meters per second. So the highest point, the velocity is 0 meters per second, which makes sense because at the highest point, it's changing direction, it's not moving, it's turning around. So 0 meters per second. 1 second later, we'll have a velocity of 10 meters per second. 2 seconds later, velocity of 20 meters per second. 3 seconds later, it will have a velocity of 30 meters per second. Now, 1 second before the peak, it will also have a velocity of 10 meters per second. 1 second before that, 20 meters per second. A second before that, 30 meters per second. Now I'm going to indicate my positive direction. I'm going to make up positive. This is arbitrary. You can make down positive as well, but I'm going to make up positive. So this object when it's going up, it will have a positive velocity. When it's coming down, it will have a negative velocity. Now I'm going to create a table for the time and velocity of this object. And I'm going to go up to 6 seconds. So 0, 1, 2, 3, 4, 5, 6. So it gets shot up initially with a velocity of 30 meters per second, and then it's going to be 20 meters per second. I'm going to put a positive on here just to remind us it is in the positive direction. 10 meters per second, and then at 3 seconds it's going to have 0 velocity. That's its highest point, its peak, and then on its way down it will have negative velocity, negative 10 meters per second, negative 20 meters per second, negative 30 meters per second. Now if we were to draw a graph, if we were to graph this on a velocity graph, we would start off with a positive velocity. You remember that the positive 30 meters per second. So we would start with the positive, and then it would reach a peak. At the peak, it would have 0 velocity. So it's going to look like this. So here's the peak, and then it's going to fall back down. It's going to have a negative velocity because it's moving in the downward direction. Next, I'd like to draw a motion map and indicate the direction of the velocity as well as the acceleration for this object. First, I'm going to start with the velocity vectors. Velocity vectors. Okay, so I'm just going to use a dot to represent this object as it's being shot up into the air. Here's the highest point, and even though this looks like it's falling sideways, I'm doing it this way so I don't have dots on top of each other, but I'd like you to imagine when we're doing these problems, the object is being shot straight up. Okay, so now I'm going to draw the vectors for the velocity. This will indicate the direction and also the magnitude of the velocity. So on its way up, it's going to decrease. The velocity is decreasing, and it's pointed in the upward direction. And on its way down, it's going to increase. It's going to speed up. Okay, so once again, on its way up, the velocity arrows are going to get shorter. On its going down, its velocity arrows are going to get longer because it's speeding up. Now let's take a look at the acceleration vectors. I'm going to draw my motion map of this object again. And now notice that the acceleration is constant, always down. It's always going to be down. What is the acceleration? What is the number for each of these? You probably could have guessed it. It's going to be 10 meters per second squared. So every single one of these, at any point in time, this object will have an acceleration of 10 meters per second squared, even at the highest point. Even at the highest point. The velocity is 0, but at the highest point, the acceleration is still 10 meters per second squared. Now let's take a look at a situation where you're throwing an object down the cliff. So you're going to throw it down with the initial, so it is still going faster, but you have an initial velocity. Let's say this initial velocity was 15 meters per second. Okay, so what would the velocity be 1 second later? It still has an acceleration. Okay, let's make down positive. It still has an acceleration of 10 meters per second squared. Yes, 10 meters per second squared. So 1 second later, it's going to be 25 meters per second, and then it's going to be 35 meters per second, and then 45 meters per second. I'm going to draw a table once again, time and velocity. I'm going to go from 0 to 3 seconds, and we start off with a positive 15 meters per second, positive 25 meters per second, positive 35 meters per second, positive 45 meters per second. What would the velocity versus time graph look like for this one? So we are making down positive. However, it has an initial velocity. So it's going to start not from the 0, but it's going to start from above the 0 here. And it will still have a slope of 10 meters per second squared. Okay. But the difference from what we saw earlier is that this one has an initial velocity because it is thrown down rather than just released and dropped down.